Hi, my name is Cindy Cross, and I am an employee here at Johnson Space Center, and I work in thermal control systems, and today I'm going to give you a little background on myself and what constitutes thermal systems. I was actually born in Bloomington, Indiana, and lived my early years there in Indiana. I earned a Bachelor's of Science in Mechanical Engineering from Purdue University in West Lafayette, and then I joined the Johnson Space Center through the co-op program and was hired on full-time after formal graduation there. Later on, I earned a Master's of Science in Systems Engineering from Stevens Institute of Technology, which is actually in New Jersey. And then I've worked as the Active Thermal Control Subsystem Manager on the International Space Station for about 10 years after I started full-time at Johnson Space Center. And at that time, we signed the contract with Lockheed Martin to develop the multipurpose crew vehicle, and I moved from the International Space Station program over to MPCV to become the Active Thermal Control System Manager, which I've been for the past 9 or 10 years now. And the picture on the lower right-hand side there is a picture of some of the Boilermakers who work on the Orion program, and I'm there right in the middle of the flag, and right next to me is actually the chief engineer for the MPCV program, and right behind her is actually the program manager for the MPCV program. So Purdue University is well represented within the Orion program. So what are sources of heat when we're talking about space vehicles? You have the computers that run the vehicle. You have the batteries that power everything on the vehicle. You have cameras and lights and exercise equipment and fans and pumps, and even the people inside the vehicle also put off heat as well. And so even if they're not exercising, just breathing and eating and hanging out, you give off heat as a person, and you need to ensure that you know how to keep that person comfortable. We also have to think about heat coming from the sun, which is a pretty obvious one, but also the Earth. The Earth gives off its own amount of heat when you're orbiting the Earth. The moon gives off a lot of heat, actually. It reflects a lot of solar energy. And when you're on the surface of Mars, you'll have to worry about heat coming off of the surface of Mars. So the job of the thermal control systems are to ensure that all of the hardware, all the structure, and the people stay within their safe operating temperature limits during all the phases of flight. So during the launch phase, when you're orbiting the Earth, when you're going between the planets, and when you're actually coming in back through the atmosphere, and when you're in the landing phase, when you may be either in the ocean or on the land. So you've got to make sure that you manage temperatures throughout the entire phase of flight. So how do we do that? So here on Earth, the way we do that is in your house, you maintain your thermostat at about 70, 75 degrees Fahrenheit, depending on how cold-blooded you like to be. And the protective environment of the atmosphere on Earth actually means that our temperature that we're trying to cool from is somewhere between 80 to 90 to 100 degrees Fahrenheit, depending on what time of year it is. We do the same thing in our cars, right? We have an air conditioning system in our cars that keeps everybody at a comfortable temperature. So how do we do this same thing in space? Well, the environments in space are a lot different than they are on the ground. In fact, when you're between the sun and the Earth, and you can see the sun, the temperature that you're trying to control against is about 300 degrees Fahrenheit. And you still want to keep everything at about 70 degrees Fahrenheit, just like we do here on the Earth. When you're on the other side of the Earth and the Earth is blocking you from the sun, the temperatures that you now have to protect against are around -2. They can be as cold as 250 degrees Fahrenheit. So you have these very extreme temperatures now that you are trying to keep your equipment and people all nice and comfy cozy at about 70 degrees Fahrenheit. So before we can talk about what kinds of devices you use to control the heat transfer, the temperatures, we need to know how you actually transfer heat from one thing to another. And there are 3 main forms of heat transfer. The first one is conduction. And conduction is simply heat transfer based on thermal conductivity of a material. And there's an equation there that shows you that it's based on the thermal conductivity of the material, the surface area over which you are conducting, and then the temperatures by which you want to you want to go between your hot temperature and your cold temperature. The best example of conductive heat transfer is when you put a metal spoon in a hot water. Your metal spoon is going to heat up. Metals are very, very good conductors of heat. They also happen to do electricity as well. So if you want to move heat from one place to the other, you want to have a very good conductor. If you want to keep heat away from one area, then you want to have what we call an insulator. And so you look for conduction properties of materials that either aid you in transferring the heat or impede you in transferring the heat. The example I have on the slide here is the candle with a metal rod. If you stick a metal rod in a candle, then the heat, you will eventually feel the heat from the candle because the rod is very conductive. The second form of heat transfer is convection, and this is heat transfer that's based on the movement of a fluid. It also has an equation that is based on a heat transfer coefficient, which is dependent on the fluid that you are trying to move. In most cases, when we think of convection, we think of air convection. We think of the fan blowing on a hot day. So the fluid that we're moving in a fan is air. You can also move liquids. You can also move, actually, you can move liquid metals. So there's a lot of different things that you can use for your convection coefficient. And then the final form of heat transfer is radiation. And radiation is heat transfer that's based on radiation exchange between two objects. And that equation is based on the surface properties of the material, so how much it wants to absorb heat or give off heat, and the area at which you're trying to transfer that heat out of, as well as the, my computer went away. So the third form of heat transfer is radiation, and that is heat transfer that's based on radiation exchange between two objects. Radiation is based on the optical surface properties of the material that you are trying to exchange heat with. And you'll notice here that the temperature portion of this equation is actually based on a power to the fourth. What that means is that radiation is actually a very inefficient means of transferring heat. You need very large temperature differences, or you need very good optical properties or very large areas. So radiation heat transfer is very difficult to achieve here on the Earth without high temperatures. An example of radiation heat transfer is the feeling that you get off of a surface that's red hot, like in front of a fire. You'll often feel the heat, and that's mostly radiation that you're feeling. If you have an electric stove and you see that it's the burners are red hot, and you can feel that heat coming off, that's radiation heat transfer. So you have conduction, convection, and radiation to work with to move your heat around your systems. And here on Earth, heat transfer is dominated by conduction and convection. We have lots of natural convection. We have wind. We have fans that we can use. Gravity actually helps us a lot in forming natural convection currents. In space, however, because we don't have air and everything is operating in a vacuum, on the outside, heat transfer is dominated by conduction as well, but to get it away from your spacecraft, you have to rely on radiation, which requires large surface areas. So what forms of thermal controls do we have in space vehicles? We have high temperature thermal control, and usually these consist of what they call the thermal protection systems. It's a very unique name, thermal protection systems, but that is specifically meaning TPS, or typically the re-entry thermal control systems that you see. Those are usually tile or ablative systems used for re-entry. You can see in the picture there, the shiny silver surface on the bottom is actually the heat shield for the Orion vehicle. That heat shield is what is used to come in very, very quickly through the atmosphere. It heats up very, very hot, over 3,000 degrees Fahrenheit, and keeps the rest of the crew module, including the crew, cool during re-entry. This piece of hardware right here is an example of the heat shield or the thermal tiles that were used on the underbelly of the space shuttle for the exact same purpose. During re-entry, this surface gets very, very hot, but the inside surface stays very, very cold. It's a very good insulator against very high temperatures. So TPS is used in a lot of different places on a space vehicle, and that's used for high temperature surface control. The other form of thermal control we have, we call it passive thermal control. Passive thermal control is used mainly in multi-layer insulation, thermal control coatings and paints and tapes, and so you just change the surface properties of your surfaces on your vehicle. I have an example of multi-layer insulation. Again, it's multi-layer because you have various layers of different material. Typically, they're very shiny because you want to reduce the heat transfer in. You want it to reflect out. You have some separators to keep the surfaces from touching so that you can reduce the conduction through the insulation. So this insulation is used, again, to keep the heat in where you want it to stay and not go outside. The best example of insulation or multi-layer insulation is actually the spacesuit itself. The spacesuit, that outer cover is a beta cloth covering that's very tough. It's a very tough white material, and that helps for micrometeoroid protection. So if small particles impact the suit, it has a very difficult time of creating a hole. But underneath the beta cloth layer is the multi-layer insulation that's used to actually provide the temperature control for the astronaut in the spacesuit. The silver surface on the heat shield that you saw before is another form of passive thermal control that helps keep the temperature of the tiles and the sealant in the tiles within their temperature limits prior to re-entry, so that that system is working properly during re-entry. And the final form of thermal control that we use on space vehicles is the active thermal control system. And this is where I work on a daily basis, is on the active thermal control system for Orion, which is pictured there in the upper right-hand corner. Active thermal control uses pumped fluid loops with cold plates and heat exchangers and radiators and sublimators to actually move heat from where it's generated through the avionics or from the people to the outside where you can reject it to space. And some of the hardware that we use for that, you can see in the picture there on Space Station. We have the 6 radiator panels that stick out into space, and we actually radiate from both sides of that, so you can see how we need a very large surface area to do heat rejection. The space shuttle on the inside of the payload bay doors is where the radiators were for the space shuttle, and this is a cutout of the space shuttle radiator. You can see it's very thin, and you can't feel it, but I can show you it's a very light structure. The space shuttle actually used Freon to flow through these manifolds, and then from the manifolds it would go across the radiator panel, across the payload bay door, and it would radiate its heat to space. And so the hot fluid would come in one side and the cold fluid would go out the other side after it had exchanged its heat through radiation. Again, it's the optical surface was chosen specifically for heat transfer capabilities. And then on Orion, we use propylene glycol and water inside of the crew module for our heat transfer fluid. And so this is an example of propylene glycol that we mix with water. On the outside through the radiators, we're actually using a fluid that's called HFE 7200, hydrofluoroethyl. And it has a much lower freezing temperature, so that when we're in our cold orbits, we don't actually freeze and turn into ice and shut the system down. Other things that we use in the active thermal control systems are cold plates. And so this is an example of a cold plate, which is just a piece of metal, a thin piece of metal. This is actually a pretty thick one because this is just a tabletop demonstrator for us. But you run fluid tubes, and so the coolant, whether it's the propylene glycol, whether it's water, whether it's Freon or ammonia, whatever your thermal control fluid is, you pump it through the surface of this plate and you'll mount whatever you want to cool, whether it's your computers or your batteries, or your display units that the crew looks at. Whatever needs active cooling, you will mount to this. And you'll come in with cold fluid and you'll leave with hot fluid. And then from the cold plates, after you've picked up heat from some of your avionics boxes, you can go to heat exchangers. This is probably really hard to see on camera, but this is a heat exchanger, and it has multiple layers in here, very small layers. And so between the internal loop that goes through the cabin where all the crew is and the external loop where all the radiators are that you see on this picture, you have this interface heat exchanger. So the water would flow through one passage and the HFE would flow through the other, and you would just, through conduction actually, conduction and convection, you would transfer the heat from the inside to the outside, and from the heat exchanger it would go out to the radiators from the heat exchanger. Now in instances where the radiators aren't used, we also have other methods of heat rejection. We can use sublimators. A sublimator is something that uses ice, and ice in a or water in a vacuum turns to ice. But in the presence of that vacuum, if you heat the ice up, it will go straight from a solid to a vapor, and that's called sublimation. And it takes a lot of heat to make that sublimation happen, so you can actually get quite a bit of cooling through that sublimation process. This is an example of a sublimator core. So the finned passages are where the coolant layer that you're trying to cool would flow through, and then the thinner layer is actually where you're building up the ice, and the ice is turning into gas and venting out to space through these passages on the side. So you have these kind of heat exchangers. Another form of heat rejection, if you can't use a sublimator or you can't use your radiator, say like when you're coming in through the atmosphere, you can't sublimate anymore because the outside pressure is such that you can't form the ice layer, you can use a boiler system. And so what you do is, this is an ammonia boiler from the space shuttle, and so in these little passages here you would flow ammonia, and the ammonia would actually evaporate. So you would boil it from a liquid to a gas, and on the outside you would run your Freon. So the Freon that was running through the radiators, since the radiators aren't cooling anymore, you run it through this boiler and it would evaporate the ammonia in here, and so the ammonia gas would come out the other end and the cool Freon would go back to the rest of the vehicle and continue providing cooling until the crew is able to get out of the vehicle. So those are some examples of heat transfer hardware that we use in the active thermal system, some of the passive heat transfer materials that we use, and some of the really high temperature heat transfer materials that we use on a vehicle. So that was just a quick explanation of thermal systems on spacecraft. So if there are any questions, I can't wait to hear them, and I'll try and reply as soon as I can. Thank you.